So let's start by looking at the question we left off on Friday's lecture. So we want to know how these concentrations can affect the overall rate and by how much. So we want to look at how the concentration of ClO2 affects the rate and OH minus. So we're given 3 experiments. If we want to look at the effect of ClO2, we are probably going to use experiments 1 and 2 because the concentrations of ClO2 changes, but the concentrations of OH minus or hydroxide does not. So the effect on the rate is only from changing the ClO2. So if we look at this, we're going to look at calculating M, and we did this in class, so this should be review. So finding M, we're going to look at the rate over rate. And so we always want to put the larger number on top, so that would be rate 1 comparing to rate 2. And we see that the concentration is 0.06 molar over 0.02 molar, all raised to the M factor. The rate here, if we find the rate, that's going to be we said 0.0248 over 0.00276. So when we divide, we have 3 to the 3.0 times, or to the m power, and we found that this was 8.99. We took the log of both sides. And then we can bring the m down, so that's all multiplied by m. Following the sig fig rules that we just learned, we have 3 sig figs in 8.99, so our decimal is going to have 3 sig figs. Here we have 2 sig figs, so our decimal will have our answer will have 2 decimals. And when we solve, m is equal to 1.99, and we're going to round that to 2 because we're dealing with integers. For the n, we're going to do a similar technique, rate over rate. Now we're going to look at rate 3 over rate 2, because the bigger number is on top. And all of that is raised to the n value. When we substitute the rates in, we had 0.00828 and 0.00276. This came out to be a nice value of 3 is equal to 3 to the n value. And so in order to make this true, n is equal to 1. So we have the general formula where rate is equal to k value times our ClO2. Our order for m is the second order, and then we have OH minus raised to the first order. So the next thing we need to do is find k. And we can actually do this by using any of the experiments, but let's just do experiment 1, Well, we know that rate is equal to K ClO2 to the second power and OH minus to the first. Using the data from experiment 1, we see that the rate is 0.0248. And we have our K. Our concentration for ClO2 is 0.06 squared. And then our concentration of hydroxide is 0.03. And if we solve this, then K is equal to the rate over the concentrations. And if we take a second to look at the units, we see that we have molarity per second, so we can bring that down. And then we have molarity squared times molarity. And so we can see how one molarity cancels. And so our K value is going to have units of 1 over molarity squared seconds. And this makes sense because we are looking at a different order. So remember that K will always have different units based on what kind of overall order you have. So here we have 2 plus 1. So we have a third order. So that means all third order reactions will have a K unit of 1 over m squared s. So if we go back to our calculations, when we plug and chug, you get a K value of 230 with correct sig figs. So now we can say our rate law is equal to 230, putting the units in, ClO2 squared and OH minus. Part C on the question is just asking for a plug and chug. So we know our K value, we know our equation. So we have 230 times 0.010 squared, because that's the concentration of ClO2 or chlorine dioxide, and 0.025 molarity. And we have a rate of 5.75 times 10 to the negative fourth. Our units cancel out, where we have meter squared, molarity squared. So we have molarity per second. We don't want that right now. Okay. So what we can do now is look at how these rate laws are impacted with the overall order and the change in rate. So remember the sig fig rules. Okay. This is just a reminder. We covered that in class. So if we look at a first order reaction, this is just methyl isonitrile becoming acetonitrile. We can relate this process and decomposition, and there's a lot of math, and all of this is basically just saying I know my rate law and I know my rate. Okay, this would be more of the average rate. How do I relate them? And so we can rearrange these equations and solve for or like integrate them. And what we're solving for is basically how does the concentration change over a course of time? So the rate equation, the average rate equation, relates our concentration to time, but it does not account for the rate order. Our rate law looks at the speed with K and the rate order, but not time. So we're just relating the two, so that way we have both the concentration and the time and the rate order. And so the takeaway message is really just this, just what's in the red box. And this is the equation you'll need to know. And this is for the first order. So you do not have to integrate anything. You do not have to know how we got to this point. You just need to know this equation. I included everything else so that way you can see kind of that we're relating the average rate calculation to the rate law. And we rearranged this form in such a nice manner to create a line. So if we look here, we have y equals mx plus b. And chemists love lines. And so from plotting the natural log versus time, what we can get is the slope and the y-intercept. So we can get the starting concentration and we can get K. So instead of doing comparing the experiments and running the average rate calculations, we can make a plot of concentration versus time. And we can see that if we just look at concentration, in this case, we're looking at gases. And remember that we can just say that this is concentration, okay? We can see that concentrations versus time is not linear, okay? Your rate changes over the course of time. If we plot the natural log of concentration over time, we get a linear fit. So we can backtrack and get the initial concentration and the rate constant K using the natural log plot. And I would say that this is an answer to some of the beginning questions. So look at number 9 and 10. Okay. We can also look at zeroth order. So remember that the zeroth order is saying that you can change the concentration, but it's not going to affect the rate. Okay. And so here we can see that the rate law for zeroth order is just related to K. So if we plot the concentration versus time, we can see that it's going to be a straight line. Okay? We can still get the K value from the slope. And so this is, again, just plotting the concentration versus time. On this graph, we have the zeroth order and the first order. So you can see that we're looking for linearity. So if you were given two different plots, you're basically looking to see what forms a line. Here, we plot the concentration versus time. And I think I actually have it already in a red block. Yeah. And we can still get our y equals mx plus b out of it. Okay. We can also look at the second order. And the second order can be done either looking at two different reactants or one reactant squared. And mathematically, once we add more reactants, it gets really crazy and complicated. So we ignore the two reactants, two first order reactants, and just look at the rate, the second order rate law with respect to one reactant, so A squared. And here, when we do our derivation, we come out to have the equation 1 over AT is equal to KT plus 1 over A naught. And again, some things that still keeps coming up. We have your y equals mx plus b, yx plus b. Okay. You have your initial concentration at time 0, and you can find your concentration at time t, and your slope is still the k. However, please note that this time your slope is positive because now we're dealing with inverses. So you think about taking the inverse of a large number versus a small, and it varies.